everybody. So today I wanted to talk to you about kinetics and review what we did in class today, and then also talk to you about some factors that we didn't discuss today. So in class we had a reaction where we took aluminum and copper chloride and we reacted them under different conditions. We did hot versus cold to show the effect of temperature, and what people came up with was really impressive. They talked about how when you have a higher temperature, the particles are moving faster. They're going to have more collisions, the collisions are going to be more powerful, and you're going to get a faster reaction that occurs. Now also what we talked about was concentration. And depending on which class you were in, we did either concentration first or temperature. This happens to be from the later class in the day. So I did temperature with them first and then concentration second. And so in this reaction with concentration here, what we see is that if you were more concentrated, the reaction reacted faster compared to less concentrated where the reaction was slower. And so, in this case, what we came up with was the idea about the number of particles. And as there was less particles in one test tube, there were less chances for a collision to happen, so we had a slower rate. If you had more particles, there were more chances for collision at a faster rate. Notice the difference when we describe this concentration versus temperature. With temperature, we're talking about the energy of the collisions and the number of collisions. Here, we're just talking about the number of collisions. Then we did a catalyst reaction where I used either a reaction with a catalyst or without, and we saw that the catalyzed reaction happened faster. So what we're going to learn about as we go through this chapter is what catalysts do and how they affect something called the activation energy, which I did mention briefly with you today. Now we looked at these factors so far. We looked at temperature, we looked at concentration, which, by the way, concentration gets this symbol in brackets and its molarity. And then we also looked at a catalyst. Well, what other factors could actually affect a reaction rate? Well, we're going to discuss a couple of more. But what I wanted to also tell you about was this idea that particles must do something in order to react. And in each class, people mentioned this, and this was collisions. And so you must collide in order to react. Now, not every particle that undergoes this collision, this process of colliding, will actually react. And that's because some reactions are not effective. You need something called an effective collision. And an effective collision is a collision that results in a reaction. And there's two main factors that will decide if a collision is effective. The first one is, does it have enough energy? If the particles don't collide with enough energy, then they won't react. And then the second thing is, do they have the correct orientation? An orientation just means position. When particles collide, sometimes the bonds need to be broken or formed, and if they're not in the correct position, then they will not react because they will not be able to break a bond or form a bond like they're supposed to. Now, I would know these things really, really well, what an effective collision is and how it works. And we can go back to our analogy that I used about the gymnasium and discuss it there and talk about, hey, people are moving really slowly. The chances of them actually colliding with one another would be really, really slim. If they weren't able to make that interaction where we said hand on shoulder, if that would not happen and the Velcro from the hand wouldn't stick on the shoulder, then you wouldn't react and you would have an ineffective collision. So, what are some important factors that we haven't discussed before? Well, one of them that came up was surface area. And people were good on this one. When I asked them, well, what's going on? Both of the people who answered in both classes, they talked about how there's an increased amount of exposed particles. And now these increased amount of exposed particles, now they can react. So we have an increase in concentration, basically. Another thing which people had mentioned, but I sort of ignored because we weren't dealing with gases, is pressure. And this is really for gases only. But when we increase the pressure, it's decreasing the volume, which is really increasing the concentration. And that's going to lead to an increased rate. And finally, something else that comes up quite a bit is nature of reactants. If we had something like aqueous ions, well, these reactions occur very fast. In fact, they are normally precipitation reactions. Precipitate means to occur quickly. And this has to do with the fact that they have a very low starting energy required for the reaction. So they have low activation energy. They're also close to one another. You know, they're in a very small volume. If you had something like gaseous particles, they're in a very large volume. They need to first find each other before they can react. Yes, the aqueous ions need to find each other, but they don't have to travel nearly as far to do that. Okay, we designed our own experiment in class to test this, and we're going to do that on Wednesday, or whatever our double period is. But what I wanted to talk to you about, because we're going to do some of this tomorrow, is, what or how we map out a reaction. How do we express, why some reactions happen faster than others, and how do we show it on a graph? And one of the main things that happen is this thing called the activation of the reaction and activation energy. It is given the term EA like this, activation energy, energy of activation. And this, the definition of it is the energy required to start a reaction. And in class, please ask me, because I'm going to do it anyway, but ask me, can you do the demo for activation energy? Because I'm going to do two reactions with you. I'm going to do the potassium permanganate, and I might have shown this one to you before. It's really cool. It's this plus glycerin. And then I'm going to do magnesium and oxygen. And what I'd like you to do is, and we'll do this in class together, but I want you to tell me which one, after you see the reactions, which one has the higher activation energy. And how do you know? How do you know which one has a higher activation energy? And we'll discuss that. Okay, so let's talk a little bit more about activation energy. Why does it exist? Well, let's say, for example, that I had some hydrogen and some oxygen, and I wanted to form water. Well, my hydrogen, I have my H's bound together like this. And my oxygens, I have my oxygens bound together like this, and then I'm going to form water. And this is sort of a throwback back to the bonding chapter, because this might remind you of BARF, break, absorb, release, form. Breaking bonds, you absorb energy. Releasing energy, you form bonds. So look at what I have to do in this reaction. I have to break this apart. To break these H's and these O's apart. This is my activation energy right here. My activation energy is the energy to break apart those bonds. And what do? I form the bonds. I form new bonds. Those H's and O's, they have a choice. They're going to either go back to the way that they were, they're going to be two H's and two H2s and an O2, or they're going to form new bonds. And this has to do with stability. It turns out that the H2O is more stable than the H2 and the O2, and that's why this reaction occurs and stays like it is. But activation energy exists because it's the energy to start the reaction. The energy to start the reaction is the energy to break the bonds apart. Now, how do I show this graphically? It's called the potential energy diagram. Potential energy diagram is going to look one of two ways. It's going to either look like this, or it's going to look like this. I know it's probably the weirdest graph that you've seen. On the y-axis is potential energy. On the x-axis is time. And these graphs look pretty much the same. There's a slight difference between them that's really the starting point and the ending point. So if we look at the graph on the left, we're starting here as reactants, and we're ending here as products. So it started off higher energy, ended lower energy. This is called an exothermic reaction. Exothermic, we release energy. If I was writing out a reaction for this, it would look like this. Reactants form products plus heat. The heat would come out as a product. This is exothermic. Over here, this graph, we still have reactants and products, except now this is endothermic. It's actually absorbing energy. And this looks like here, reactant forms product, but the product that it's forming is higher in energy. So to show that, we would have reactant plus heat yields product. And that's what we see when we have an endothermic reaction. The reactant, we add heat to it, we form a product. On the left side, we have a reactant forming a product, and we're giving off heat. There are reference tables that talk about this. Now, you'll be required to actually know 6 arrows that go with this. If we draw out our exothermic reaction here, we have 6 arrows that we're expected to know. Arrow 1, arrow 2, arrow 3, arrow 4, arrow 5, and arrow 6. And these are the 6 arrows that we're expected to know for this. Besides the fact that it's exothermic. What are the 6 arrows? Well, I'm going to list them for you, and then I want you to go through your textbook, and I want you to define the terms here, and then we're going to practice some of this tomorrow. So term number 1, it points to the reactants. It's the potential energy of the reactants. 2, potential energy of the products. 3, right here, it is the potential energy of what's known as the activated complex. 4, it is the delta H, the heat of the products minus the heat of the reactants. In this case, when it's negative, it's exo. And we can write that up here, negative delta H. If it was endo, it would be positive delta H. 5, activation energy. There's that energy to start the reaction. And then 6, reverse activation energy. That would be the activation energy if you were going in reverse. The energy if you were starting as the products and ending as the reactants if the reaction was reversible. Those are the 6 arrows. I recommend that you memorize them and that you know them. What we'll do next time, and I want you to sort of do this on your own, heat or reaction, exo, endo, activation, energy, activated complex, look these up, look them up in the textbook, know the definitions. I'm going to ask you about them in class. And what I'm going to do during the next video is talk about how to do a catalyst with these, and also how to use table H, and then talking about Hess's law. We'll do that for our next video. All right, thanks so much for watching.